Okay, so absolute value equations and inequalities. We're going to kind of use everything that we've learned so far about equations and inequalities and look very specifically at one type. Before we do that, we're going to decide, is this inequality sometimes, always, or never true? And just as we've done, anytime you have a problem like this that looks real long and complicated, we're just going to simplify it. So let's start on the left side. We're going to distribute that positive 3 to my two terms, which are positive 5 and negative 2x. 3 by 5 is 3 by 5 is 15. 3 times negative 2x will be minus 6x. So that's my simplified left-hand side. And then to the right, I don't have to distribute, but I can combine those like terms. I've got 1x and minus 7x. So 1 take away 7 will be negative 6x. And then I have the minus 13 still remaining. Here I can see I have negative 6x on both sides, so I know it's going to be one of those weird, like either always true or never true. So I add 6x to both sides. I end up with the statement 15 is less than or equal to negative 13. Clearly 15 less than or equal to negative 13 is not true. So that means this inequality is what we call never true. There is no number you could replace x with to make a true statement. It will always be a false or not true mathematical statement. All right, now let's remind ourselves what the heck is absolute value. So absolute value is denoted by these vertical bars. And they kind of are treated like parentheses as far as like PEMDAS, but there are some pretty important things that don't work when it comes to absolute value. First of all, like by definition, absolute value is the distance. The absolute value of a number is its distance from zero. So what is the distance from zero to that number? That is the absolute value of the number. Okay, because we're talking distance, absolute value cannot be negative. I live 22 miles from Roseville Area High School. If I drive 22 miles to get to school, driving home isn't negative 22 miles, right? Just because I'm going the opposite direction, it doesn't mean the distance is opposite. It's still positive 22 no matter what. So the idea of absolute value and it being a distance means it has to always produce a positive number. So if you have an expression like this, negative 6 times the absolute value of 4 minus 7, again, we kind of have to treat absolute value like parentheses, and they shoot up the list to very top of the priority and order of operations. So 4 take away 7 is negative 3. So what I end up with is negative 6 times the absolute value of negative 3 after my first round of simplification. Now we just ask ourselves, what is the absolute value of negative 3? What is the distance from negative 3 to 0? And the answer is positive 3. So now since I took the absolute value of negative 3, I can just put 3 in parentheses, and negative 6 times 3 is negative 18. Okay, so we are simplifying the expression that's inside the absolute value, and then once we get it down to a single number, we're going to take the absolute value of that number. So if we look over here, the absolute value is not just a single operation, but it's two operations. It's 6 minus 2 times 4. That is still going to follow the order of operations. So I'm going to multiply first. So 6 minus 8, because 2 times 4 is 8. Okay. I'm not ready to take the absolute value yet, because I can combine 6 and 8, or 6 take away 8 to be negative 2. The absolute value of negative 2, what's the distance from negative 2 to 0? And the answer to that is 2. And then I can add 12 finally at the end, so 14 is my simplification. So if you are evaluating or simplifying an expression that has absolute value in it, you're going to kind of focus on that piece first and get it down to just be a single number. Okay. If we have absolute value in an equation, one way to look at this is I could say the absolute value of what number is equal to 15. What could x be so that if I took the absolute value of that number, I would get 15? And for a lot of us, the first answer that jumps out right away is, well, if I took the absolute value of 15, if x was 15, then clearly we would have a true statement. But it's not the only solution. What is the other number that if I took the absolute value of it, I would get positive 15, and that other number is negative 15. So there's a couple ways that you'll write this. You could just leave it x equals negative 15, x equals positive 15. Sometimes you'll write it with a comma in between. This is how Math Excel likes to write their solutions, negative 15 comma positive 15. And if it's the exact same number, just one positive, one negative, sometimes you'll see this symbol, which means both positive and negative 15. Any one of those three ways of writing the solution is fine. What you'll see is that the third way of writing, the plus minus 15, does not work if we have something like this. The absolute value of y minus 4 equals 10. Now, how we're going to do this is like, if I cover this up, let's do this temporarily. If I covered up what's inside the absolute value, you all saw it was y minus 4, but let's just pretend, for the sake of conversation, that you don't know what's in there. Well, what single number could be under the green blob so that the absolute value of that number is equal to 10? There's only two options. It's either positive 10 underneath the green blob, or it has to be negative 10. Now we know it's not just a number, it's actually the expression y minus 4. So what we're going to do for this is we are going to actually split this equation into two separate equations. And what I mean by that is we know that the expression y minus 4 has to either equal positive 10, so that the absolute value of y minus 4 is 10, or the expression y minus 4 would have to equal negative 10. And this is an or problem because either one is going to work for us. So y minus 4, the part inside the absolute value, either has to equal negative 10 or it has to equal positive 10. And from here, I'm just going to use my algebra to solve each one of these equations individually. Here, to get y by itself, I would add 4. You do need to be careful because when I add 4 to negative 10, I'm going to get negative 6. Here, if I add 4 to both sides, I get y is equal to positive 14. So that means if y is positive 14 or if y is negative 6, I will get a true mathematical statement. So my solutions are negative 6 and positive 14. Okay. Clearly, because 6 and 14 aren't the same number, I couldn't use the plus or minus symbol in this case. So most of the time, I'm going to write it with a comma in between, kind of like that. Okay. So if there are multiple steps going on in an absolute value equation, we're going to focus on getting the absolute value part of the expression by itself first. So I'm going to isolate the absolute value of x plus 3, and I'm going to do that by doing the same steps that I would do if it was just the letter x. Sorry, I dropped the pen. So here, if I want to get x by itself, I need to get rid of that negative 2 in front, and I need to get rid of the plus 11. Now, one thing I didn't mention is you cannot distribute across absolute value. So if it was negative 2 times parentheses x plus 3, I could distribute the negative 2. We actually cannot do that with absolute value. There's a small time that you can get away with it, but we're going to just, instead of playing like you can do it here, but you can't do it here, we're just going to get rid of that negative 2 another way. Before I do that, this would all be considered one big fat term. So I need to subtract 11 as my first step. I want to subtract that constant 11 from both sides. If I do that, I now have negative 2 times the absolute value of x plus 3 is equal to negative 10. Okay. Great, we're one step closer to getting the absolute value by itself. Now I'm going to get rid of the negative 2. This is multiplication. It is multiplication out front. We just can't distribute because it changes the values of some numbers. So I'm going to divide both sides by negative 2. When I do that, my negative 2's undo each other here, and I just have x plus 3 is equal to positive 5. And now I'm ready to split this up. I know that, again, if I play the little marker game, oh boy, it's going to be aggressive. If I cover this up, what's underneath the green blob has to either equal positive 5 or it has to equal negative 5. So I'm going to split this equation into two separate equations. One situation where x plus 3 is equal to the negative 5, and one where the x plus 3 is equal to the positive 5. Now you'll notice when I split this up, what is no longer in the problem? Those absolute value bars. Okay, so by splitting this into two equations, I'm effectively undoing the absolute value, and I don't no longer need those absolute value bars. Here, I can get rid of plus 3 by subtracting 3 to both sides. I get x equals negative 8. If I subtract 3 to both sides here, I get x equals positive 2. You can just leave it like that and box it in if you want. Otherwise, I'm going to say x is equal to negative 8 slash or comma positive 2. So those are my two solutions to this equation. If I go back and replace x with negative 8, I will get a true statement. If I go back and replace x with positive 2, I will get a true statement. Go ahead and try this one on your own. Pause the video, and then we will keep going. Okay, the absolute value of x. So here's the part I want to isolate. There's a lot going on inside the absolute value, but it is being divided by 4. So my first step before I can split this is I need to undo division by 4, and I'm going to simply multiply by 4 on both sides. Okay, so if I do that, I divide by 4 and multiply by 4 to undo each other. I would then have the equation absolute value of 2x plus 1 is equal to 12. Now that the absolute value has nothing outside of it on the left side of the equal sign, I am ready to split this into two equations. So the inside of the absolute value, 2x plus 1, either has to equal negative 12 or the inside has to equal positive 12. And now I'm just going to, again, solve these two individually. By subtracting 1 from negative 12, I'll get negative 13. And if I divide both sides by 2, you could call this negative 6.5 or you can call it negative 13 halves. I'm just going to leave it a fraction. If I subtract 1 here, 12 take away 11 would be, 12 take away 1 would be 11. Getting ahead of myself. Again, divide by 2 on both sides. 11 divided by 2 is 5.5, or you can call it 11 over 2. So a couple options here. You could do negative 13 halves, comma 11 over 2, which is how like a Math Excel or most programs would want you to type it in. Or you could say x equals negative 6.5, comma 5.5. Both are exact answers, so we are good in either sense. Okay. So get the absolute value by itself, then go ahead and split it up into two situations. Now, all of those examples that we did had two solutions. Okay, negative 13 halves and 11 halves. What else do we have? We had negative 8 and 2, negative 6 and 14, negative 15 and positive 15. When would be a situation where you wouldn't have two solutions? Pause and see if you can figure out what situation would allow you to not have two solutions. There's actually two situations here. Most of the time, the absolute value expression is equal to a positive number. You will have two solutions, such as x plus 1 is equal to 7, positive 7. One of the other possibilities is what happens if the absolute value is equal to 0. So, for example, the absolute value of x plus 1 is equal to 0. What would x have to be in order to make that a true statement? Well, in this case, the only way that I could get the absolute value of x plus 1 to equal 0 is if x was the number negative 1. And there's no other solution for that problem. There's no other number that would work for that. So in this case, if the absolute value is equal to 0, you will have exactly one solution. And maybe you can guess what the third line is from here. The third possibility is what happens if the absolute value is equal to a negative number. So for instance, the absolute value of x plus 1 is equal to negative 3. And the reason this isn't possible, and this confuses students quite a bit, because up here, if you split this into two equations, you have x plus 1 equals negative 7 and x plus 1 equals positive 7. The issue with this is that if I take the absolute value of a number, we just said earlier, absolute value of any number will equal a positive value or at least 0. In this case, I'm asking you to figure out how to make absolute value of an expression equal a -3, and it is not possible for the absolute value to give you a negative value. So if you find yourself in this situation, this equation has no solutions. There are no ways to get absolute x plus 1 equal to -3. You can have solutions that are negative. What I can't have is absolute value equal a negative number, because then that cannot possibly happen. Okay. So that is kind of the rundown of absolute value equations. Now, if you have the same variable on both sides, okay, we're going to kind of have the same setup. It's just a couple more steps. Um, so this is saying the absolute value of 2x minus 3, and I want that to equal 4x plus 1, or sorry, 4x minus 1. Now, what we would have done in the past is we would have minus 2x from both sides, but we can't do that because the absolute value bars are around the expression 2x minus 3. So what do? We're going to split it up just like we've done into two equations, one where 2x minus 3 is equal to something, and another one where 2x minus 3 is equal to another something. Okay. Now, if we take a look back real quickly, what we did was when we split this up, this was positive 12. So one equation was equal positive 12, the other equation was equal negative 12. Okay. So whatever was on the right side of the equation or across from the absolute value, one equation was equal that number, the other equation was equal to the opposite of that number, so negative 12. We're going to do the same thing here. The problem is 4x minus 1 isn't a single term. It's actually two terms, right? 4x and minus 1. So one of my equations is going to use the exact same thing, 4x minus 1. But the other equation is going to be the opposite of 4x minus 1. Now, what the heck is the opposite of 4x minus 1? It is just the opposite of each term individually. So what's the opposite of 4x? Negative 4x. What's the opposite of negative 1? Plus 1. Okay. So in the right-hand side, or in one of my two equations, this matched perfectly. On the other side, I am flipping the sign or taking the opposite of both of those terms. And notice 2x minus 3 is staying the same for both of them. Now that I've split it up, I can drop the absolute value bars and I can start manipulating these things how I want. Okay, so here I would take the lesser of the two x's would be 4x. I'm going to use color here. So I'm going to add 4x to both sides, add 4x to both sides. I get 6x minus 3 is equal to positive 1. I'm going to then continue by adding 3 to both sides. 6x is equal to positive 4. My final step would be to divide by 6. X is equal to 4/6, which is a fraction, would actually reduce to x equals 2/3. Okay, so for the time being, that is one solution. The other solution is what I get from solving here. Now the lesser of the two x's would be the 2x, so I'm going to subtract 2x from both sides. Negative 3 is equal to 2x minus 1. I'm then going to add the 1 to both sides to get to negative 2. And finally, divided by 2, negative 1 is equal to x. So right now, as it stands, our two solutions are negative 1 and positive 2/3. But what we just said on the previous slide was that absolute value cannot equal a negative number. Now, the problem with this is I don't know if 4x minus 1 is negative because presumably I don't know what x is. So here's what we need to do. We need to make sure that of our two solutions, I need to make sure that when I plug in these two values for x, when I plug in 2/3 or when I plug in -1, I need to make sure the quantity for x minus 1 is positive, because I can't have absolute value of something equal a negative number. So what we need to do is we need to replace this x with 2/3 and just make sure it's equal to a positive number. So 4 times 2/3 is actually 8/3, which is like 2.6 repeating. Minus 1 is going to be 5/3, which is 1.6 repeating. So this solution is good. What that means is if I replace x with 2/3, I will get a true statement in the original equation. Now what happens with -1, if I take the expression 4x minus 1 and I replace x with -1, okay? If I replace x with -1, 4 times -1 is -4, take away 1, and that is -5. This is bad news, because what that would be saying is I have absolute value equal to -5, and we cannot have absolute value equal a negative number. So what that means is that this solution is actually not a real solution. There's a word for it. It's called an extraneous solution. It's a solution that like algebraically you get an answer to, but when you go back and plug it in, it doesn't make sense. So in a problem like this, okay, if you have the absolute value of x and then it has x on the other side, you need to go back and check your answers. At least, at the bare minimum, you have to make sure that when you replace x with the number you found, that you get a positive number on the across from the absolute value. Okay, we'll do more examples of this, but I just want to kind of show you one of these if the variable is on both sides. Okay, how we're going to wrap this up is we're going to just real quick apply absolute value to inequalities now. So if I showed you this, if I said what numbers could x be so that the absolute value of x is greater than 12? So the distance from 0 of that number is greater than 12. There's actually two options here. I could have x is greater than 12, right? 13, 14, 15, 100, 3 million. But those aren't the only numbers whose absolute value is greater than 12. There are also the negative numbers, -13, -14, -15. And those numbers can all be described by the expression or the inequality x is less than -12. So as long as my value of x is one of these two categories, as long as it's either less than -12, so to the left of -12, or it's greater than +12 to the right, this is going to make a true statement. So we have, just like we did yesterday with the compound inequalities, we have an or situation. X needs to be less than -12, anywhere out here, or x has to be greater than +12. Okay, x has to be greater than +12, which means anything out to the right. So in between -12 and 12 is bad, but anything outside of the 12s will give me a number whose absolute value is greater than 12. So we're splitting it up just like we did with equations, but now we're just putting the word or in between them. If it's greater than, because if I ask a similar question, say, what values of x could I take the absolute value of and get something less than or equal to 8? Well, there's two possibilities. X would have to be less than or equal to 8 for sure. But if I just put that on the number line, x is less than or equal to 8, this is bad because this goes on to the left forever, into the negatives, towards negative infinity. Okay, so not only does x have to be less than or equal to 8, this stops at some point, and the point it stops at is -8. I need a number in between -8 and 8. So what that means is I have to cut myself off and say the only numbers whose absolute value are less than or equal to 8 lie in this range between -8 and 8. So this half of the picture looks like x is less than or equal to 8 because it's shading to the left from -8. But this half of the picture is shading to the right from -8, which would be x is greater than or equal to -8. It's a lot of 8s. I just said right there. Now here's the thing. Both of these statements have to be true. The number you pick has to be less than or equal to 8, and it also has to be greater than -8. So instead of using the word instead of using the word or to connect these inequalities, we are going to use the word and. So if you have a absolute value greater than, we're going to split it up just like we did, but you'll notice in the first example on the right side, I have the exact same carbon copy, and on the other side, not only did I flip the 12 to be negative, but I also, because I multiplied by -1, I had to switch the greater than to less than. Okay. Over here, x was less than or equal to 8, or absolute value of x was less than or equal to 8. So when I split this up, one of them matches exactly, and the other one, I flip the 8 to a negative, and because I do that, I have to switch the less than or equal to greater than or equal to. So it's kind of a lot going on there. But if we just write this out in general, if you have absolute value of x is less than a, just some random number a, you will split this up into x has to be less than a and x has to be greater than -a. Okay. So when we split this inequality, one's positive a, one's negative a, just like we did. But when you have the negative a, you have to flip the inequality as well. So the less than becomes greater than. Or on the other side, if I reversed it, when I split this up, x is greater than a, so I'm just copying everything the same. Or x has to be less than -a. Again, a turns negative, and then I shade the other direction. So if I put this on a number line real quick, x is greater than a would be open circle shading towards the right. X is less than -a would be open circle shading towards the left. If I have an and inequality, okay, I need x to be less than a, but I also need x to be greater than -a, so I kind of get this in-between shading business. Okay. So that's kind of the generic form when we split this into two inequalities. Okay. Now, if you would like, you can pause the video. Using what we just covered, you can try to set this up into two. You could try to solve this inequality that has absolute value in it. I'll go through it, but if you don't want to work on the example and you just want to shut off the video, feel free. You're free to go. Okay, if I wanted to solve this inequality, okay, I would need to first isolate. The rules are the same, even though it's an inequality. I have to isolate the absolute value. Okay, so what I'm going to do is I'm going to subtract 9 from both sides. And then that would give me absolute of 5 minus 2x over -3 is less than or equal to -5. The absolute value is almost by itself, but I have to get rid of the -3, so I'm going to multiply by -3 on both sides. Because I'm multiplying by -3 on both sides, I get to flip the inequality for the first of like 3 times. -5 times -3 is positive 15. But I switched the less than or equal to greater than or equal to, and now I have absolute of 5 minus 2x. Okay. So now that the absolute value is by itself, we are ready to split this up. So if we look back at our graphic organizer we just made, greater than or equal to 15 looks kind of like this. So we're going to use the word or in the middle. Okay. So if I want to split this into two inequalities, I'm going to have 5 minus 2x is greater than or equal to 15, or 5 minus 2x is less than or equal to negative 15. So those are my two options. So now we're just going to solve each one individually. I'll start on the left. I'm going to subtract 5 from both sides. That's going to give me negative 2x is less than or equal to negative 20. And then just for fun, I'm going to divide by negative 2. Because I'm dividing by negative 2, that less than or equal to has to switch back to greater than or equal to. So I get x is greater than or equal to positive 10. Or over here, I could do the same two steps. I'm going to subtract 5. When I subtract 5 from positive 15, I get 10, which is kind of nice. Negative 2x there. Divide by negative 2, divide by negative 2. Oh boy. Again, we switch the inequality, so x is less than or equal to negative 5. So this right here is my solution. X has to be greater than or equal to 10, or x has to be less than or equal to negative 5. If I was going to throw that on a number line real quick, I would say here's 0, here's 10, here's negative 5. In orange, we have x has to be greater than or equal to 10, or x has to be less than or equal to negative 5. If you stuck around this long, congratulations. Hopefully this was a fun little challenge for you.